Today, we are going to present to you light and optics laboratory practices for the subject Physics for Engineering. Our team members are Jorge Acevedo, Alexa Canché, Osvaldo Chan, Carolina Garma, Guillermo Montes de Oca, and Alan Peraza. So, let's start with the first experiment.
Hello, this is an experiment in order to find the refractive index of water. Introduction. In optics, the refractive index of a material is a dimensionless number that describes how fast light travels through the material and is defined as n is equal to c over b, where n is the refractive index of the material, c is the speed of light in the air, for example, and b is the speed of light in this new material, because it actually changed. History. The phenomenon of light refraction has been known since antiquity, and Pythagoras even formalized his observations. The Dutchman Wilbur Snell made some experiments that led him to find the law governing the change of direction of light passing from one medium to another. Thus, when the physical properties of the medium in which a light ray moves are changed, there is a change in its direction. The figure 1 shows the deflection of a ray when it passes through two different media. Renatus Descartes was familiar with the manuscripts of Snell's, and his task was limited to giving them mathematical form. The Snell experimental law expresses the relation of geometric proportionality illustrated in figure 1. As we can see in the figure, there is a relation between the distance of A1 to A2 and B1 and B2 and the angle A and B. Snell-Descartes law. Descartes' mathematical formulation of the law of refraction is given by the following equation: n1 by sin of theta 1 is equal to n2 by sin of theta 2, where n1 and n2 are the refractive indexes of two given materials, and theta 1 and theta 2 are the angles with respect to the normal, as shown in the figure. And here we can also see the relation between the refractive index, which is equal to the radio of the sin of one angle over the other. And another interesting fact here is that the faster the medium is, the smaller the index of refraction gets. The objective of our experiment is to determine the refractive index of water using simple materials. There are various laboratory methods which, with the help of suitable instruments, allow the measurement of refractive index. For example, the film method using lasers, the apparent heat method using microscope, and the angle of deviation method using an spectrometer, among others. The materials used for this experiment are the following. We need to have a transparent plastic receipt, a plastic tube, a protractor, a ruler, a scissors, a little hook, a pen, and a piece of paper and cardboard. The mechanism of the experiment. With these materials, we are going to build something like this. And the first thing we have to have is a giant retractor. That's why we need the piece of paper and the cardboard in order to build it manually, or we can print in a bigger piece of paper the format. With the little tube, we are going to produce the artifact that is near to the eye, and which is gonna help us to see the refracted line that we are going to seek in the water. We have the angles. The beta angle corresponds to the angle of the air, and the alpha is for the water. The h here is the height of the water in the receipt. The procedure of the experiment is the following. When we already have the GM protector, we are going to use the piece of paper and we are going to draw a red line. After that, we are going to put the protractor in the same position as the red line as in the first image. Then, with the little hook and the plastic tube, we are going to generate this artifact here that is going to help us to see the line through it, as in the third image. Here we can see the plastic receipt already fulfilled with water, and that's me using the plastic tube to see the red line produced in the water. Then, having done the previous procedure, we are going to do something like in this video. We are going to start from the highest to the lowest point and using different angles, of course. And what we are going to see here is that the red line produced in the water differs in distance depending on the angle in which it's seen. So we are going to see again the video to see how the distance between these two lines that are the same is changing depending on the angle. So in the start is closer, but the biggest the angle gets, the biggest the distance also gets. So here in the paper you can see some annotations that I did in which for different angles, let's say 20 degrees, 30 degrees, I draw the lines respecting to the lines seen in the water. And after that, we are going to measure with the ruler the distance in millimeters for each of these lines. Finally, these are my results. I put the image of the mechanism here to remember what we did. The things that we are going to record in each observation for each angle are the following. We are going to write the angle, which is beta. That is the one that we are using for the air. So here we have 20 degrees until 70, for example. Then the second thing that we are going to record is the x distance between the original red line and the red line seen through the water, as seen in the figure. These distance are measured in millimeters. The H letter corresponds to the height of the water, which is constant and is 5 centimeters or 50 millimeters. Then we are going to make some computations in order to find the alpha angle. So for computing the alpha, we are going to use the formula that is in the right side of the table, which is arctant of x over h. This is going to give us the alpha angle in degrees. After that, we are going to make a tier table with the sine properties of each angle as seen in the image. Why do we do this? Because if you see the formula, we have that relation. So knowing that the reflective index of the air is 1, we have to move the sin of E over the sin of A in one side to have only the reflective index of water on the other side. So we use substituting the reflective index of the air, which is 1. We have the final relation, which is in the chart here, in the red square. And this is the formula that we are going to seek to find in order to compute the reflective index of water. That is the reason of why we compute the alpha angle and then the sine properties of each one, because we are going to make a graph using this relation. So here's the graph, and the graph is made in the y-axis with the sin of B values, and in the x-axis using the sin of A values. So as you can see, we have a straight line, and the equation for this line is given by this function, which is 1.27x plus 27, and 54. So from this, we can then say that the slope of this line is going to be our reflective index for the water find, found. So here we have that this index is approximately 1.27, and the original, the theoretical for the water, is 1.33. So we can see that the index found is very, very close to the original. So we can say that our experiment or our measurements were a success. So as conclusion, and having observed the results of the graph, we found the results quite satisfactory and close to the original value of the water refraction index. So we can consider this experiment a success. Among the difficulties of this experiment, it is that we have to be very careful with the accuracy of our observations as we are dealing with angles, and it is very easy to bias the results. So this is all, and thank you very much for watching. And we would like to thank the Universidad Nacional del Mar de Plata, which was the document in where we inspired this experiment. Also, we have another reference for the theory and experiment as seen here. Thank you.
Hello everyone, I'm going to talk about my experiment, visible light decomposition. First, I want to give a short introduction to this topic, and I want to start by talking about the visible light. The visible light spectrum is a segment of the electromagnetic spectrum that we as humans can see. The electromagnetic radiation is light, but we can only see a small portion of all this spectrum, and the portion that we can see is called visible light. We as humans can see these visible lights thanks to cone-shaped cells inside our eyes. These cone-shaped cells are tuned to the wavelength of the visible light spectrum. For this experiment, I'm going to take as inspiration Newton's famous prism experiment, and I will try to replicate it to decompose white light's color spectrum, as we can see in the picture right here, where a beam of white light is going through the prism and the result is all the color spectrum. Therefore, the objective of this experiment is to visualize the decomposition of white light into the full color spectrum, and to achieve this visualization through an easy to replicate experiment using common materials. I want to remark that common materials refer to things that you may have in your house, and if you don't have, you can get them from almost any store. And before going to the experiment, I want to talk about the scientific background of this experiment. The first record of a similar experiment to this one was the one made by Isaac Newton in 1665. Is the prism experiment that I just talked about, and basically what Newton did was to decompose white light into the full color spectrum. With this experiment, Newton was the first person to prove that the white light is just made up of all the colors that we can see. To clarify what I referred to with the term white light is to the light that we can see from the sun or from artificial white lights. Not from any artificial light, but they have to be white. Another important point is about the CDs. As we are going to use CDs for this experiment, I want to talk about how CDs reflect the colors of the rainbow. And this is thanks to the phenomenon called diffraction. The way CDs work is that they have really small rollings in their surface. These rollings work as a diffraction grating. When white light hits the CD, it gets diffracted, and what we see is just the diffraction pattern. Now I want to talk a little bit deeper about all this light spectrum topic. What we can see in the picture right here is the full radiation spectrum. We can see that it goes from 1 millimeter to 10 nanometers and from infrared to ultraviolet. What these numbers refer to is the length of the waves. ergo the wavelength. And what we know as visible light is somewhere in the middle of all this spectrum, specifically from the 750 to the 380 nanometers. And they can be classified according to their colors. I want to remark that all these numbers are just approximations, as we cannot say when a color ends, and if we compare the numbers here in the picture to the numbers in the table, we can see that they differ a little bit. Another topic I want to talk about before going to the experiment is how the human eye works. How can we perceive the colors as humans? And this is, as I was saying in the introduction, because we have different cells, cone-shaped cells in our eyes that help us distinguish the colors. These cells can be classified into rods and cones. The rods are the ones that help us identify darkness, like when we are inside our house and go outside in the noon, it's like so bright we cannot really see, and this is when rods are working. They are adapting our vision according to the lightness or darkness from the environment we are in. In the other hand, we have the cones that are the ones that actually help us distinguish colors. We have cones dedicated to the color red, green, and blue, and they work together to form all the other colors. An interesting thing to note here is about the colorblind people. The colorblind people are colorblind because a type of cone is not working well inside their eyes. Either the red, the green, or the blue cones are not working well, or they just don't have this type of cone. And what this causes is that they cannot perceive colors as not colorblind humans can. We can see here that there are some weird color spectrums, and this is just how they can perceive the colors if they are colorblind, according to which type of cone they are lacking. So now let's talk about the experiment. First, I want to list all the materials that I use for this experiment, starting with a CD or DVD, glue, scissors or a cutter, a LED lamp, it must be of white light, modeling clay, tape, and a piece of cardboard. Let's get right to the development of this experiment. The first thing I did was to cut a small notch in the disc. In this case I was using a DVD. The notch should reach the center of the disc, but it should not include the center. The second step was to peel the metallic coverture of the disc. If you are using a DVD, it might be of two capes, which means that if you cut this notch right here, the second cape might come out, and you can use the second cape without peeling it. The third step was that I cut a piece of cardboard and glue it to the center of the disc, because we do not want the light to go through this center. The fourth step was simply to stick the disc in the modeling clay so it works as a base. And finally, I improvised a base for the LED lamp so it can reach the center of the disc. We want the source of the light to be at the same height as the center of the disc. And now we can see the results in this video. What we see here is the white light of the LED lamp through the CD. And here's an example of the type of picture we can get with this experiment. In this picture we can clearly distinguish all the colors of the rainbow. To conclude this experiment, I want to talk again about how easy to replicate this experiment is. Anyone can do it with materials found in your home, or if not, you can easily buy them in almost any store. And with this experiment, we can confirm that the white light is composed from all the colors of the visible spectrum. Even though the light spectrum is wider than just the rainbow colors, Our human eyes cannot see the full spectrum. Nowadays, it is possible to see other parts of the light spectrum that we as humans cannot see with the help of technology. For example, with the heat sensors, we can see a different light spectrum. That's pretty much it for this experiment. I hope you enjoyed it, and we can see here in this slide all the reference and sources of information I used to make this possible. Thank you very much.
Good day everybody, this is a presentation for the homemade telescope. As a quick introduction, telescope is an optical instrument that was first designed in the 16,000s, patented by Hans Lippershey. He described it as an instrument for seeing things far away as if they were nearby. A telescope basically contains an arrangement of lenses or curved mirrors, which purpose is to collect rays of light and focus them on a way so that the resulting image is magnified. There exist many types of telescopes, but the first ones ever made were the refractor telescopes and the reflector telescopes. The one that we made is the refractor telescope with a glass lens. The objectives of this project is to design a cheap, reusable, ecological instrument to observe distant objects. For the science background, the objective lens is what's the other end of our telescope, collects the light rays from a distant object and then brings them to a focus dictated by the curvature of such lens. The length where the light is focused is what we refer to the focal length. In order for us to be able to see with our very own eyes, we use a second lens. This is called the eyepiece, and it will be at the focal plane. This eyepiece magnifies the image from the objective lens to the retina. The second lens also has a focal length, like the objective lens. Now, in order to calculate the magnification, we divide the focal length of the telescope at 360 millimeters divided by the focal length of the eyepiece, which was 20 millimeters. This gives us 18 times magnification. For materials and development, it was relatively simple. We needed a magnifying glass and a fisheye glass to make the glasses. A potato chips can, like a Pringles can, it works perfectly fine. A soda cup, we use a Burger King cup. It can be done with any kind of cup. A glue gun and duct tape and scissors in order to secure everything. For the first step, we cut at the bottom, and with the same cutting, we made the eyepiece holder. We just pierce the hole inside the bottom, and then just glue it. It fits really well. For the second step, we cut at the bottom of the Pringles can, and then we glued the objective lens to the Pringles can, and we secured it with duct tape so it doesn't fall out. Next, we just merge both pieces and add a little bit more duct tape so we cover the area that we just cut. For usage and results, the target is the plastic bag near the sofa, left of the fan, and the distance was about 4 meters. And the picture at the left is taken with 1x phone camera zoom. As you can see, you cannot really see anything. And at the right is with 8x camera zoom, and really you cannot see anything. You just see a green bag with some leaves maybe. But with our telescope, we were able to see the recycling triangle and even what it says, reduce, reuse, and recycle. So it was very, very helpful in order to see. So in conclusion, our telescope, despite its recycled materials, proved to be very effective with different target at multiple distances. We were able to calculate with a calculator and a ruler the magnification of our telescope, which varies by the focal length of the telescope divided by the focal length of the eyepiece. So that will be everything. Thank you very much for your attention and have a nice day.